Hello, biologists. Welcome back. Hope you guys enjoyed your last weekend before the start of term. I know I did. This particular lecture here on science, biology as a science, is going to be the first lecture where you're really going to be required to know things for the midterm coming up, for the first midterm. And so here we go. Let's go ahead and start out with a very simple question. What is science? Now imagine yourself standing on a street corner and a news reporter comes up to you, sticks a microphone in your face and says, "What is science?" Do you feel qualified to answer that question right now? Maybe not. And that's because what science is kind of nebulous to most people. Most people think of science as kind of like a field or an endeavor. And in fact, for many people, they consider themselves scientists by the very fact that they have the word scientist after their name on their business card. But that's not really the way that you should be looking at it. Science really is all about a process. That is to say, science really just means to know, and it's characterized by a process of thinking. That is to say, it's not a topic. Science really isn't a topic, it's just a way of thinking about the world. For that reason, anybody can be a scientist, not just those people that have it on their business card. You can be a scientist. After this lecture, you probably will be. I'm a scientist for that reason, not just because of any degrees or what my business card says, but because I think a certain way. My daughter is also a scientist because she knows how to think critically in this way. Okay, let's take a look at a couple of scientific questions, and that might actually elucidate to you what it takes to think like a scientist. All right, here we go. These are some scientific questions. Are there more tuna when waters are warm or cold? How can seals dive so long? How do pesticides impact coastal ecosystems? Okay, take a look at these questions. Think about them for a second. What is it about these questions that makes them scientific questions? And you probably already are thinking of the answer. The answer is that these are questions that can be answerable with numbers. You can go out and measure stuff and come up with some sort of response. And you can measure this actually multiple times. Measure it hundreds of times if you want. And if your answer comes up kind of the same each time, well, then you tend to have a little bit more confidence in your answer each time you do it. That's what defines a scientific question. So now the key here is that scientific questions have to be testable. That is, you have to be able to measure something about them and come up with an answer. The more technical way of thinking about this is that they have to be falsifiable. That's the term that we use in science, is that your question has to be falsifiable. That is to say, it has to be able to, well, you have to be able to demonstrate that it's not true. Another way of thinking about that, you have to be able to disprove it. Notice that that's the exact opposite of saying that you're going to prove it. In science, we don't prove anything. Very important that you understand that distinction because most people don't understand that. Scientists are not in the business of proving anything. Scientists are in the business of disproving things. So when we read that question, are there more tuna when waters are warm or cold, we're not trying to prove that tuna are responding to warm or cold. We're trying to disprove whether or not tuna are responding to warm or cold. I'm going to explain a little bit better how that works later. But very important that you understand, when anybody ever says prove, they usually are not speaking properly about science. The people who are notorious for doing this are advertisers. Whenever you turn on the television and you hear some medication advertised as science proves that this product is good for your hemorrhoids or whatever it is, you know that that statement was not written by a scientist but was written by an advertising person. Very important. Science is not in the business of proving. Science is only in the business of disproving things. And for that reason, you have to formulate your questions so that they can be disproved. Are some examples of non-scientific questions that are not disprovable. Which ice cream is better, vanilla or chocolate? Well, I guess that depends on who you ask. If you ask my wife, she'd say chocolate. If you ask my daughter, she'll say vanilla. But the point is that in both cases, it really comes down to their own personal opinion. Very hard to quantify that, which is why that's not a scientific question. It's a good question, but it's not a scientific question. What is the spiritual meaning of life? Heck, that's a question we've been asking for thousands of years, isn't it? But it's not the kind of question that is testable. It's not falsifiable, and therefore it's not a scientific question. Will there be peace in the world? Well, I sure hope so, but there's no way that we can answer that question just using science. It's not testable. It's not falsifiable. Now, science, the way that we use science is very procedural. We follow steps in science. And for that reason, it really is the best tool for answering complex questions. You're faced with complexity in the world all the time. But a good scientist, using that scientific procedure, which we're going to talk about in a little bit, allows you to cut through that complexity and actually capture the utter simplicity that is truly going on under the hood. Now, let's go over an example here. I've got the two meandering dots here. I'll explain what that name means in a little bit, but it's a really good demonstration of apparent complexity when in fact there's actually simplicity involved. All right, let's do that now. All right, so this is the screen I wanted to show you. Take a look at what's going on here. Is that not the coolest thing that you've seen all day? Okay, so what if somebody was to ask you to describe for them what's going on here? Do you think you could do it? What are those dots doing? Are they traveling randomly around? Are they traveling at the same speed? Does one dot have anything to do with another dot? Okay, now as you're staring at this, you're probably recognizing that every now and then a pattern emerges somewhere, and then maybe it disappears. So, is it fair to assume just by staring at this that there's actually some underlying thing going on here that just might explain the complexity that we appear to be seeing? Of course, the answer is yes, but the question for you is, how do you get to that point? You see, this is the difficulty that a scientist faces every single day. Somebody who was not scientific, somebody who just marveled at this without really caring to know what was going on and simply said, "Wow, that's really neat. I wonder how that's happening. You know what? It's too complicated for me. I choose not to know how it works. I'm just going to be content to marvel in how cool it looks." Okay, that's fair. But the scientist would look at this and go, "Wow, that's really cool. I wonder how that works. You know what? I'm going to see if I can find out." So for a non-scientist, what you're looking at here on the screen is the end of the conversation. That's just really neat. But to a scientist, this is the beginning of the conversation. This is neat, and I want to know how this works. So, how would you go about describing this? Well, there are many different ways you can do it. I'm sure you're already thinking of some of them. Heck, let's track one of those dots. Pick a dot on the screen. Here, let me see if I can throw my mouse in here, and we'll pick a dot together. How about that one right there? It's traveling. We kind of get a rate of speed, and it hits the wall, and oh, it bounced off the wall. Well, that's interesting. At least we know that these dots are not just meandering into the field, right? I mean, they're all kind of contained in there. At least if you followed enough of these dots, that's what you'd find out, is that they're all contained in there. Are they all behaving in a similar way? Are they all bouncing off the walls in a similar way? Well, actually the answer is yes. Are they traveling at different speeds? Kind of, but in a way that you can actually measure. They travel in a range. So, now I want you to imagine what a scientist could do with this information. If you were to track the movement of all of these dots in space and then get kind of an idea of where every single one of them is moving at any given time, and then use a computer to track all that stuff backwards in time, I wonder if they would all kind of emerge from the exact same event. This is exactly what scientists try and do, is pull out some simple explanation that can explain how you might arrive at what appears to be complicated. Alright, are you guys ready to kind of see what this is like from like time zero, if we were to actually backtrack this all the way to the beginning of time? Let's do that. Here we go. Okay, so I just reset the field here, and this is the surface of a planet, let's say. Alright, everybody go ahead and pick up a virtual rock or a little stone or something like that in your mind. And what you're going to do is take it and throw it at the screen on the count of 3. Okay, are you ready? 1, 2, 3. It's a wave function. This is a wave that is traveling out from a little tiny disturbance, and I have set it so that the rules tell it that when you hit the wall, to just bounce right back. Okay, this is just a model, but it's a good model for demonstrating a very important point. You see, a wave function, we don't even need to go over the mathematics of it, but you can kind of get the idea that the math that describes the movement of a wave is actually very simple. But if you take something that is very simple and you put it into a simple kind of a computer model like this, and you just kind of let it run, within a matter of 30 seconds or so, that very simple function ends up producing apparent complexity, when in fact this is not complicated at all. Every one of those dots is responding and behaving in a way that can easily be predicted if only you knew what the initial conditions were in the very beginning. You don't always know what those initial conditions are. Sometimes, and in this case, there's only a few variables here. It's just a simple wave operating in a box. Imagine the natural world out there with more than just walls around this confine. Maybe there's temperature issues. Maybe there's light-dark issues. Maybe there's pH issues. There's all kinds of issues that are acting on these little organisms that are behaving just normally. And what is truly amazing here is that now you know precisely what led to this complexity. You know exactly what led to this. But now imagine being a scientist where for your career, your job is to essentially take a snapshot picture of this screen and use that snapshot to try and explain what led to this apparent complexity. That is what science is all about. We don't stop at just saying, oh yeah, that's really interesting, that's really cool, but I choose not to know how it works. I would rather live in ignorance than to actually know how it works. That's what you guys are going to be doing this semester. You're going to be looking at these sorts of things, and I'm going to be asking you to be critical about them and to open your mind to new explanations for how the natural world actually works. Okay, let's continue on. Well, I hope you enjoyed the 2 meandering dots. I had promised you that I would tell you what that title means. 2 is the name of the last name of my brother-in-law. Yeah, my brother-in-law is a computer programmer, and he made that little program for me just so that I could show it to you. Isn't that nice? Let's move on. using this scientific procedure, which we're going to formalize a little bit later as the scientific method, maybe you've heard of it, this procedural way of going about thinking as a scientist has led to some pretty incredible discoveries, some major scientific discoveries like these. These are concepts in science that are very, very important, because every time we go out and try and measure something in one of these fields, it always seems to point to the same answer over and over and over and over again. So, for example, the way that the ground moves seems to be consistent with everything we know about plate tectonics. The way that electrons travel all seems to agree with what we know of electricity. And, of course, the devastation of splitting the atom, we certainly do know about that one. We're going to cover some of these things in our class. Quantum theory, not going to cover that one. Just thought I'd throw that up there for you. But we are going to cover genetics and evolution by natural selection. These are all very important concepts in science. Now, we rely on the scientific method, and we rely on measurements. Anytime you have the opportunity to measure something, you should do that. And you don't want to just rely on your eyes, because sometimes your eyes play tricks on you. And that's why we rely on rulers and those sorts of things that we can use to measure. Let me give you a couple of good examples of why you don't necessarily want to rely on your eyes alone. I've entitled this slide, Why Humans Believe Weird Things. Kind of a funny one here. Let's talk a little bit about pattern recognition. This is completely unrelated to the actual science we're going to do later. I'm just trying to make a point here. Take a look at that picture. You guys notice anything in that picture? It's obviously grass. It's a picture of tall grass. How many of you see the face in there? Can you see the face? Hopefully you can. You probably can. In fact, I'm pretty darn sure you can. In fact, you're looking through the grass, and you can probably see that it's not just a face, it's a lion, or at least a big cat. And there's a reason why you can see this. Let's rewind 2 million years ago. Let's imagine that you are a proto-human standing on the plains of the Serengeti in tall grass, and you are kind of stumbling along in the grass, and you don't see this face. For some reason, you can't see it because the pattern looking through that grass is just too complicated. Your brain can't process it. So you're walking along, and where are the offspring? You know, if this was your ancestor, let's say, where are the offspring of this ancestor that can't see the face? All right, well, the descendants, the answer is that type of a person wouldn't have any descendants. Why? Because they'd be lion food. 2 million years ago, you walk by a face like this and you don't see it, you're lion food. So if you couldn't see this, you weren't able to have any babies, and therefore your likeness would never be transported down through time. Okay, what about the human 2 million years ago, the proto-human that's walking along and can see that face and pauses and goes, oh my goodness, well, maybe it's a lion. I don't know, I can't tell. It might be a lion, but then again, maybe my eyes are just playing tricks on me, so I'm going to stand here and just wait. If it moves, then it's a lion. If it doesn't move, well, then maybe it's just a figment of my imagination. Yeah, where are the descendants of that person? You probably picked it out. The descendants? No descendants of that person. Why? Because he was lion food too. You see, anybody that would stop and wait to see if it was a lion, if they were right, they'd be dead. Okay, so now I want you to imagine this scenario of 2 million years ago. You're that proto-human walking along, and you see that face. You recognize it as a face. It may be a figment of your imagination. It may be a real lion. It doesn't matter. You're going to run away from it anyways. Where are the descendants of that person? Well, they're sitting in your seat. You are the descendant of that person. You see, it doesn't matter if that is a real lion or not. If you ran away from a fake lion, you're still going to be alive. If you ran away from a real lion, you're still going to be alive. Why am I even telling you this? Well, because hardwired in your brain is the remnants of that survival instinct. We see faces in everything, whether there's a face there or not. When you look out your car window when you're driving wherever it is you're driving, you recognize faces of people because they really are faces. But the outcome of that, like an artifact of that, is that sometimes you look at things that are not faces at all, but you see a face because it's hardwired into your brain. It was a survival skill of your ancestors of 2 million years ago to run away from faces or to respond to faces whether there were faces there or not. What the heck is he talking about? Let me show you an example. How about this video? Let's play this video.
Sometimes, the little things in life feel like our biggest enemies.
You guys see the faces there? How about that one? How about that one? Is there an actual face there? Okay, you're like, yeah. No. That's not a face. That's a hanger. Yeah, that's an iron. But you see a face anyways. You know in your mind that that is not an actual face, but you see it anyways. Because it's programmed into your brain. It's hardwired into your brain to see faces even when there aren't any there. How about that? And what's amazing is that the advertisers for American Express, they knew this, and they used that to try and get you to buy credit cards or to get credit cards. kind of bizarre. Anyway, the point is that programmed into your brain is the ability to see faces even when there aren't any. And for that reason, we see faces in everything, including in cheese sandwiches. This here is a picture from the backside of Mars. This also is from Mars, different scale though. And this is on a cliff face here. I believe that's in Utah. I'm not exactly sure, but I think it is. And here's an outcropping that looks like a profile, doesn't it? Here's the nose, here's the mouth and the chin. Are these actual faces? I hope you answer no. No, they are not actual faces, but you see them there. So, your eyes, in this case, are telling you that there's something there that actually isn't there. Again, this is why we rely on measuring tools instead of just relying on our eyes. Let me give you another example of that. Here's that same picture that was taken from Viking 1, which was a satellite that we sent out to take pictures of Mars. And man, when this picture came back, people had all kinds of Martian stories. Oh, the Martians are there, and they're building monuments to humans, and they're trying to communicate with us. No. Let's go ahead and zoom in. You see, we went back in 2001. We sent another probe back there to take a picture of that same mountain range, and there it is. There's no face there. It's just a mountain. In fact, it's just a hill. And that hillside right there is miles across. So, is there a face? Well, you know what? Squint your eyes. If you squint your eyes as you're looking at that screen, you almost can see that same face come back out. But it's important that you understand that the only reason you're seeing a face when you squint is because by squinting you're removing information. You're making it low resolution. In science, we clarify things by gaining more information and by getting higher resolution, essentially, imagery of things. So there is no face there. It's just a hillside, and yet our brains still see a face. Now, here's another example. How well can you catch details? This is really important. I'm going to show you this video here. Some of you may already have seen this. If you haven't, well, you're going to be in for a treat here. You guys see there's actually players there, some wearing black t-shirts and the others are wearing white t-shirts. And what they're going to do is they're going to be mulling around among themselves. And the ones in the white t-shirt are going to be passing a basketball back and forth to each other. And as they're mulling around, the guys in the black shirts are going to be doing that too. But I want you to focus on only the three people in the white t-shirts. Only the white t-shirts. They're passing that ball. back and forth, and they're going to be mulling around. Your job is to try and count the number of times that the ball is passed. You might think this is easy, but it's actually not. And I'm going to give you guys a little bit of a caveat here. It turns out that there's a difference between males and females in their ability to see how many times this ball gets passed. So really concentrate on just the guys in the white shirts, and we're going to count, and then I'm going to give you the answer afterwards, and you'll be able to see whether you were right or not. Okay, are you ready? Let's go ahead. Click. Ready to count? Here we go. All right. How many did you get? Did you get 14? Did you get 15? Did you get 16? The answer is, it doesn't matter. It doesn't matter. What did you guys miss? How many of you saw something really weird and peculiar going on while whoever they were, the black shirts, the white shirts, were passing the ball? I'm guessing that there's at least a couple of you out there that saw something really strange. Did you guys see the gorilla? You're like, what? What are you talking about, gorilla? Are you kidding me? All right, let's rewind this. Let's play it over again. And this time, I want you to not pay attention to the people in the white shirts. Just kind of stare at the back of the walls. You know, look at the elevators in the back. There's people in black shirts, people in white shirts. There's an S on the wall in the back. There's a floor down there. Nothing all that interesting. Oh, what's that? Hey! It's a gorilla! It's a guy in a suit. Now, some of you are like, wait, what's the big deal? I saw that all along. But you know what? Not everybody did. In fact, the majority of people watching this probably didn't see it at all the first time through. That's right. It's kind of strange. It happens that way, and it's because some of us lack the ability to concentrate really hard on any one thing. Most of you that could concentrate didn't see the guy in the monkey suit. Only those few of you that have a hard time concentrating were able to see it the first time through. Believe it or not, this guy, Daniel Simons, he's actually a psychologist at the University of Chicago, and this video was put together to kind of demonstrate the ability of people to concentrate. So there you go. Kind of neat. Okay, so that was kind of interesting. What is the point? The point is that for that faces video, in that section that we talked about faces, that's an example of you seeing things when they aren't actually there. This monkey example is you missing things that were right in the front of your eyes. So again, if we just rely on our senses, on our eyes, sometimes we miss things, and sometimes we misinterpret things and think we're seeing things that actually aren't there at all. This is the value of science. This is why we rely on using scientific inquiry for things that we can actually measure. Let's go back to the actual scientific method now and look at it in a little bit greater detail. The scientific method, how does it work? Well, there are steps involved, and these are the main steps. Sometimes people will break these out and make more, but you know what? That's just adding complexity where it's not necessary. These are 5 really solid steps for the scientific method. The first step is observation. You actually go out into the world and make some clever observation that interests you. From that observation, we then formulate what's called a hypothesis. A hypothesis is really your best guess Based on what you know, it's the most tentative explanation that you can come up with. Now, your hypothesis may not be right. Sometimes it's right, sometimes it's not. The point is that you've posed an idea with your hypothesis. You've posed the best idea you can come up with, and then you design an experiment that tests the hypothesis. After you have run your experiments, you gather your results, you analyze your results, and then you draw a conclusion. Point is that your conclusion, the conclusion that you draw, isn't until the very end. And actually, that's another big difference between science and non-science. In non-science, the conclusion is usually all the way up here before the observation. And then what happens is you make an observation and you try and explain it away because somebody has already given you the conclusion. That is not how science works. In science, we draw our conclusions only after we gather our results. In a little bit greater detail, it looks a little bit like this. Observations, we simply walk out there and go, I wonder why plants are green. That's kind of an interesting thing. I have no idea why. So I'm gonna try and find out why. So observations lead to questions. Now, how are we going to address why it is that plants are green? Who knows? Maybe plants are green because some little dude comes along and paints them green every morning before I get there. So that's my hypothesis. It's my tentative explanation. So I'm going to then design an experiment and collect some results that test the little man painting the trees hypothesis. I'm going to set up a hidden camera right outside my office and take a look at that tree outside there and see if that's what actually happens. And lo and behold, I look at my camera when I come into work. There's no little man there. Tree's green anyways. Okay, so obviously my hypothesis was incorrect. I have disproved my hypothesis. It means I got to come back and reformulate a hypothesis. Maybe it's that these things are green because they contain some sort of a pigment that helps them with photosynthesis, as we're going to find out later. I could run all kinds of experiments, chemistry experiments, that in fact demonstrate that it's a pigment that makes them green, and so that's how I'm evaluating my hypothesis, and I come up with my conclusion at the end. Does my conclusion support my hypothesis? If it supports it, fantastic. What if it doesn't support it? Well, then you start over from the drawing board and reformulate a new hypothesis. You do that each time. Now, in a little bit greater detail, let's go ahead and come up with an example, something that you might be able to identify with. Okay, maybe not you, maybe somebody you know. The effects of alcohol. Maybe you have a friend and so you understand this empirically. So, observation. Let's make an observation. I'm going to go ahead and start out by giving you an observation. How about this one? Drunk people tend to stumble. All right, you know it's true. You've seen your best friend at a party. Drunk people tend to stumble. That's my observation. So let's come up with a hypothesis, something that explains this observation. You could come up with a million of them. It has to do with alcohol, so I'm going to make something up. Maybe it has to do with, stumbling has to do with coordination. So let's go ahead and say something like, alcohol consumption reduces coordination. Notice it's a little bit of a statement. I'm stating alcohol consumption reduces coordination. Am I right? I have no idea. We haven't tested it yet. This is just my hypothesis. This is my working idea that I think best explains this observation here. Now, it's not necessarily correct. It's not necessarily true. It's not necessarily proved. Remember, we don't prove things in science. It's simply my best idea. So I'm going to go ahead and set up an experiment. How are we going to do this? I know you're all thinking about it. It's obviously going to have to involve drinking here. So maybe you shouldn't be doing the experiment. You should be measuring this in some of your friends. Let's go ahead and remember we want to measure somebody who's been drinking versus somebody who hasn't been drinking. But in fact, let's go ahead and control even better. Let's go ahead and measure somebody before drinking, and then measure them after drinking. So we'll test coordination before and after drinking. We'll see, we'll get to the bottom of this. And let me go ahead and just give you the pretend results here. Let's pretend that the person scores significantly lower after drinking. They're far less coordinated after drinking than they were before. Okay, what conclusions can we draw? Well, we can conclude that obviously drinking has something to do with the loss of coordination. We may not know precisely how, but we know that there's some relationship going on there. So, has our hypothesis been supported by our results? The answer is yes. Our hypothesis is supported. However, did we prove that alcohol is the factor? No, we did not prove it. We simply weren't able to disprove it. So it withstood our test, and there are many confounding reasons why we can't necessarily just rely on our results. What did we not account for? Can you think of anything that we haven't accounted for here? Well, how about the fact that some people handle alcohol differently than others? We didn't account for the weight of the person. We didn't account for their age. We didn't account for male or female or their experience with alcohol. We didn't take into account whether they ate before or not. So these are all confounding variables. So what we do is we go back and we re-ask a new hypothesis. And when we set up our next experiment, we try and control for one of those factors. Now, if it keeps turning out that those people who drink score significantly lower regardless of whether they're male or female, regardless of what their age is or their weight or all of these other factors, then that is to say, if we can't disprove this hypothesis a whole bunch of times, we tend to trust it. After a while, we trust it. When you gather a lot of evidence, you tend to gain a lot of trust. When you only have a little bit of evidence, you only trust it a little bit. See how this works? So, in science, the amount of trust you place in your hypotheses is determined by the amount of evidence you have, the amount of experimental evidence that backs up that hypothesis. I haven't been able to disprove it yet, and I've tested it hundreds of times, and I still can't disprove it. I therefore accept it more and more. We haven't proved it. Remember, we don't try and prove anything. We only try and disprove. So, here are some important considerations. You see, when we do our science, you could be the smartest guy in the world. It doesn't matter unless you tell people about it. So, scientists also have to be very good writers. Why? Well, because if you share information, you share scientific knowledge, it could lead to further research and further discoveries. We allow our peers, our other scientists, friends, and sometimes not our friends, but we allow other scientists to evaluate and critically and critique our work. It's important that we do that. We never keep things secret in science. Everything is open access. Everything is freely available. We also write down our procedures so that other people can repeat them. If we're going to make an extraordinary claim, we discovered some new thing, we better document how we discovered it, so that here we are in Santa Ana. Maybe our friends in Sweden would like to duplicate our experiment to see if they come up with the same results, and that's why we share our information as well. And this could have all kinds of important implications for humans and for the planet. So we share that information. So the question is, well, how do we share that information? Well, we share it in peer-reviewed journals. That is to say, we share it in written journals that are reviewed by anonymous peers. That is, before it gets published, it has to go before anonymous peers who get an opportunity to rip it apart if they don't like it and send it back to you and tell you to rewrite it. Or they accept it and maybe they'll ask you to revise it before it gets published. Very rarely does it ever get published without even needing to be revised. That rarely happens. And so since we have so much fact-checking in science, it means that you tend to trust much of what is published in the peer-reviewed journals because it's gone through that peer review process. Now, is it true that junk can get published? Yes, on occasion that does happen, but the vetting process is pretty darn good in science. We also present our results at scientific conferences, and heck, we call each other on the phone and email. That's actually a really good way to communicate. Now, how is science done? Remember, we're making careful observations and measurements, and we interpret our results after and only after we have collected our data, never before. And, we also have a very high standard in science for the cutoff for when we will accept something as good and when we don't accept something as good. So the question is, how accurate do results have to be in science for us to consider them scientifically valid? That is to say, there's always error in measuring stuff. So how much error will we accept before we tell the person, you got to throw it out, you have to remeasure it, you have to do it over again? The answer is, and I haven't written this down anywhere, so only the people who are listening to this lecture are going to get this, 95%. You have to be accurate 95% of the time in order for it to be considered scientifically valid. That is a very high percentage of accuracy. In other words, if you're only accurate to within 93% in science, that's considered not good enough. You got to throw it out. Interesting, isn't it? So let's go ahead and compare scientific versus non-scientific information, just as an endeavor for discovery. How about this one? Let's go ahead and make some observations and ask some questions. How about something like this? Will it rain on my wedding day? This was absolutely something that my wife was really concerned about. I'm guessing some of you are married out there, and this probably was a concern of yours too. Well, who did you consult? If you wanted to know if it was going to rain on your wedding day, what did you do? Did you go to this guy? Hopefully not, right? He's a soothsayer. He's the guy that looks in a crystal ball to tell you whether or not it's going to rain on your wedding day. Is he going to be right? Maybe. In fact, he probably will be right as often as you'll be right. How about this one? I'll make a prediction from you, from my office. Who knows where you are? Maybe you're taking this class and you're in Phoenix, Arizona. So how can I make this prediction? Well, because I don't know, almighty, and somehow I have that brainiac power. Okay, for those of you that plan to get married in July, and you're going to do it, let's say, in Phoenix, Arizona. Hold on, let me consult my crystal ball here. No, it's not going to rain on your wedding day in July in Phoenix, Arizona. How did I know that? Did I divine it? Is it that I'm just this amazing voodoo witch doctor? No, it's based on experience, of course. And maybe that's where this crystal ball guy gets his information. The point is, you don't know where he's getting his information from. And for that reason, you shouldn't trust it. Here is where I would consult if I wanted to know if it was going to rain on your wedding day. That's right, a satellite image, because this is information that's being gathered every 2 minutes of every single day from a camera in outer space. I'm going to trust this because I know exactly how it's being gathered, and I know the limitations of it as well. So I trust satellite images for predicting whether it's going to rain or not. How about this one? You might say to yourself, well, of course that's obvious. Nobody's going to go to a soothsayer or a crystal ball reader, right? You'd be surprised what people still do these days. In fact, certain countries, you might go, well, that's silly, right? There's no such thing as sorcery or witch doctors or anything like that. Oh, yeah? Well, go to certain countries, Saudi Arabia, for example. They're actually executing people for practicing magic and sorcery. That's right, you probably are sitting there in your seat going, magic and sorcery, that's silly. You're right, it is silly. And yet, countries are executing people for claiming to practice it. This is not just, something that I pulled off of some obscure journal. I pulled it out of the Washington Post. And this is from December 12th, so this is just, Not that long ago, December 12th, 2011. Kind of insane, right? But you might think to yourself, oh, well, that's Saudi Arabia. That's not going to happen here in the United States. Or is it? That's right, folks. The United States is not immune to that kind of silliness. Let me show you. In fact, I'm not going to show this to you here. I'm going to provide the link underneath this this video demonstration, and you can go to the YouTube video and actually see what's going on with witch hunters in the United States. It's really actually quite amazing. Okay, so let's come back to some scientific questions here. When you are sick, who do you consult? Who do you go to? Well, hopefully you go to your doctor. All right, that's not really my doctor, but I wish it was. But the point is that you go to a doctor for a reason, right? You go to a doctor because they have knowledge. That's right, they went to med school. They learned about whatever ails you, okay? And are they going to know everything? No, and in fact, they'd be the first to admit it, right? They are really good at certain things, and when they run across something that they don't know about, what do? Well, behind their desk in their office, they've got a huge library of books to consult with, right? And they'll track it down, or they'll contact a colleague, or they'll do something to try and come up with an answer. But one thing they will never do, or at least they shouldn't ever do, is make something up. Because if they make something up, they're opening themselves up to all kinds of liability, right? So a doctor is going to rely on all that education they got and all of those resources and references they have. And that is why you trust doctors when you get sick. When you get sick, I urge you to please not call Miss Cleo. She's not going to be able to divine what's wrong with you. That's just the facts. Okay, let's look at another example. Are humans causing the Earth to warm? This is another really important one that's been in our media for the last, few decades now, but certainly over the last 5 years it's been a hot-button controversial issue. How about this? Here's a person standing in front of her raised Hummer, kind of interesting, and she goes, like, no way, oil companies, the former president, and Senator Inhofe say it's fake. Okay, so you know who I mean by the former president, George Bush, and Senator Inhofe is the honorable senator from the state of Oklahoma, both of whom are global warming deniers, and while they don't have any actual scientific backgrounds, this is the perspective that they are taking. So do you accept this, or do you accept that nearly all climate scientists in the world have concluded, based on their scientific research, based on their hypothesis testing and their experimentation, that all seems to point to the exact same cause, that humans are in fact causing global climate change? This is a really important one because the media, who are largely ignorant of science, feel obligated, since they don't know themselves, they feel obligated to get two sides to the story. In this case, there really isn't two sides. There's only one side to the story, and that side is the side of evidence. Scientists we don't make things up. We can't. Our careers are staked on the claims that we make, and the claims that we make are based on evidence. When we have lots of evidence, we trust this a lot. When we have only a little evidence, we trust it a little. In this case, you have independent scientists in independent fields, hundreds of them, writing thousands of papers every single month, and they all seem to point to the exact same cause. So the reason why we trust that human-induced climate change is a fact is not because we want to believe it, but because that is what the evidence is telling us. So that's kind of critical here. Now, you might ask yourself, well, what's the difference between science versus non-scientific points of view? Are they both equally valid? Well, when it comes to answering questions, I would argue that the scientific method is far better. And we have to follow very strict rules that non-scientists don't have to follow. Like, number one, we can only have a strict view of reality. We can't make stuff up. And remember, it's a structured process of gaining information. If you don't follow the procedures, then people are not going to trust your science. So let's start off with that reality issue. What is reality to you? Well, if we want to understand the natural world, we need to ask this real question. What is the real world? What does it mean to be real? Well, in science, it's very clear. The real world, to a scientist, is made of two things, and two things only: matter and energy. And when it comes to interpreting or measuring things in science, we're either measuring matter or measuring energy, or the change of matter from energy, or the change of energy to matter. One of those sort of things. We can never measure things that are outside of matter and energy. That makes up the entire living world. So, what is the real world to a non-scientist? Well, to a non-scientist, they're not beholden to only matter and energy. It allows you to go beyond the obvious. It allows for spirituality, for things that are unknowable, and we marvel at things that we don't know about. And because of that, things like hope, imagination, emotion, belief, faith, supernatural phenomena, we allow those things, if we are non-scientists, to affect our own reality. But as a scientist, you cannot rely on any of these things. None of them are measurable. None of them reside in the here and now of matter and energy. So, I want you now to kind of change directions here, just briefly. Let's talk a little bit about what we know. And, is what we know today everything? Are there discoveries to be made later? Well, obviously, yes, there are. Let's stare at a picture together. Look at that. Isn't that a beautiful sunrise? This is actually a picture taken up, I believe that's Tahoe. That's Lake Tahoe. It's gorgeous, right? There's a waterfall there, and that's a sunrise. Now, let's ask yourself, we call that a sunrise. Is the sun actually rising? You got to think about this for a second. Is the sun rising? The answer is no, it's not. In fact, the sun is fixed in our solar system in the middle, right? And we are the ones that are moving, right? We're moving around the sun. However, from the vantage point of where you're standing in this picture, it looks as though the sun is the one that's in motion, and we feel like we are stationary. Now, for those people, who were around 500 years ago, that would not include you or me, but for people who were around 500 years ago, that assumption was not set in stone, right? And were they wrong? Yes, they were wrong, but does it matter? Not really, because by going by the assumption that the sun is the one moving in the sky, it was good enough for figuring out when it was time to plant your crops, when it was time to go to bed, when it was time to wake up the chickens and feed them in the morning. All of those important things for survival and human civilization worked just fine when we used to think that the sun was actually going around the earth. So we need to be careful. We can't necessarily get down on those people who lived in the 1700s, let's say, who used to think that the sun revolved around the earth, because they were simply operating on the current level of knowledge. Science is a process of gaining more knowledge, and basically what it came down to is they were making conclusions with a much smaller library than what you have. So, just kind of a case in point. Oh yeah, look at that. Let's go back 2,000 years ago. So the people who were around the Roman times, or even before that, back in the Greek times, to them, the sun was actually a god that was being pulled through the sky. Now, were they wrong? Of course they were wrong, but it didn't matter back then. You see, back then, thinking that there is this god Helio that's being pulled through the sky, on a chariot, was good enough for figuring out when it was time to plant your crops, when it was time to wake up the chickens, when it was time to go to bed, etc. So, again, we are operating with a library that is much bigger than the people in the past. And just like 100 years from now, people will have a bigger library than you and I have. So they'll think a couple of things we think about are silly, like, Beyonce. You guys saw the post on the discussion board? If you haven't, go check it out. I posted a link there to a story about Beyonce. Apparently, a horsefly was named after her. Isn't that exciting? Okay, moving on. I want to introduce you to my favorite my favorite philosopher. His name is Ludwig Wittgenstein. And he was around in the 1950s, really interesting character. And, he was working at Princeton, and he had a bunch of grad students walking around, and grad students kind of think they're all that. They're, philosophy grad students. And one of his students was actually quoted as saying to his professor, Professor Wittgenstein, "Oh yeah, those medieval Europeans, they must have been pretty darn stupid to think that the sun actually revolved around the earth." And the funny thing happened. You see, Wittgenstein was a pretty wise guy. He turned to that grad student and said, "Yeah, well, I wonder what the sky would have looked like if the sun had revolved around the earth." Well, what's the answer? Well, the answer is it would have looked the exact same. You see, we didn't gain our knowledge of the rotation of the Earth around the sun by looking at the sun. We gained that knowledge by looking at the stars. That's another subject, which we're not going to get into here, but the point is, he was pointing out to his grad student, don't be so hard on those people in the past who were operating with a smaller library than you. They were doing the best they could with less information. We're all gaining more information every single day, and we therefore need to be humble as we're slogging through life. Okay, so let's come back to the scientific method. Let's recap. We've talked about what a hypothesis is, but you've probably heard the term theory before. And are these words interchangeable? Can I just call one or the other a hypothesis or a theory? No. These are completely different things, and this is something that will appear on your midterm, so make sure you can distinguish between a hypothesis and a theory. A hypothesis is simply your best guess. It is an educated idea. It's a concept. And when you have tested a hypothesis enough times, thousands of times, you can keep testing it a whole bunch of different ways. You test it from the left, you test it from the right, from above, from below. And every time you test that hypothesis, you can't disprove it. Then you start to accept it. Then you start to trust it more. Then you start to be able to make predictions off of it. Then you've got a theory. A theory is the highest praise you can ever give to a concept. If it's called a theory in science, we put the highest level of trust in our theories. Now, that word means something completely different outside of science. If you are, watching the news or you're watching your favorite TV program and they use the word theory, what do they mean? They mean a concept. They mean an idea. What they probably should be saying is hypothesis. In science, we only call things theories if we have the utmost acceptance, the utmost trust in them, and we have been able to make huge amounts of predictions off of them, and they always seem to come out as true. Let me give you a good example. Here's some scientific theories. I should define it here a little better. A theory is a generalization drawn from results of many hypotheses that all haven't been disproved, and they're very, very, very well tested. And high degree of confidence in theories, we actually allow them to dictate how we teach, in fact. We have that much trust in them, but we trust them only because of the amount of evidence supporting them. The germ theory, the theory of gravity, the theory of evolution, all of these things are core ideas in science, and they actually explain much of the field of science. And they haven't been disproved ever. So are theories ever safe from being tested? Absolutely not. You got to remember, in science, nothing is sacred, nothing is secret, and everything is fair game to be tested. If you don't like the theory of gravity, no problem. You have every right to go and test it yourself. You probably won't disprove it. It hasn't been disproved in ever, but you have every right to do that. So, theory, scientific theory. Here it's used in a really bad movie, conspiracy theory. But they're using that word in not in a scientific way. They're using it in a layperson's way, and you need to know the difference between that. And I have an example of a video clip here just because my daughter and I were watching Hulu the other day, and I wanted to show her what Japanese anime was all about back in the 70s, right? So I showed her Speed Racer. Awesome, awesome cartoon. So it's important that you understand. I'm going to show you the clip here in just a second. It's important that you understand that theories are not just speculation. They're not just ideas in science. We actually hold them at the highest level. So let me show you this Speed Racer clip, and you see if you can pick out what this guy is saying.
And because of the tremendous amount of accidents, metropolitan traffic has been hopelessly snarled.
What do you think's causing all the accidents, Speed?
I haven't the vaguest idea.
Well, I have a theory.
I figure the accidents aren't accidental.
Somebody's causing them?
How about that? So, I know you're, well, hey, that was kind of interesting for Japanese anime. Yeah, it was, that just brings me back to my childhood. Anyway, the bartender there says, well, I have a theory. Well, what does he have? Does he really have a theory? No. He's got an idea. He's got a hunch. But he is not using that word in the same way that we scientists use it. So when you hear people in the media using that word and referring to it in a context of science, you need to understand that they are not trained scientists, and that is a mistake. When somebody says you shouldn't, when it refers to like evolution by natural selection, say, well, it's just a theory, you guys. Oh yeah? Well, when we say something is a theory in science, we mean that it has the highest ability to predict things. And I'm going to give you another example of that here in just a second. Let's move on to another theory that people don't tend to question very much. Oh yeah, I should say theories are very well founded at this point. For example, the atomic theory. The idea, the concept, but in this case, the theory that everything is made up of atoms. Have you ever seen an atom? No, probably not. But because of your knowledge of what atoms are, and if you don't know much about atoms, we're going to learn a little bit about them in this class in the next few lectures. If you understand what atoms are all about, you understand how it is that all matter on the planet can be constructed by them. It works by a very nice series of logical explanations. And we'll go over the atomic theory a little bit later. Here's another one that we're going to talk about in a multitude of lectures here. The theory of neo-Darwinian evolution. Very, very important concept. It unifies all of biology, and you're going to be experts in it after this course. So, theories have predictive value. That is to say, if you put your trust in theories, you should be able to make predictions, and the outcome should be exactly what you predicted. And I'll tell you, this guy right here, this shaman, no matter how much he waves his shrunken head over that hunk of metal underneath him there, he is not going to get it to levitate. However, give me a team of nerdy engineers, I'll hand him a 2-ton hunk of steel, and they will be able to get it to levitate. In fact, here's my team right here. Okay, yeah, that came from Revenge of the Nerds, one of my favorite movies. But look at the bottom there. That's 2 tons of steel levitating. And guess what? We levitate 2 tons of steel hundreds of times every single day. And we have for almost 80 years. So this, every time an airplane goes up in the sky, it is further confirmation of the theory of gravity. So these are predictions, and this is why we rely on science. Science is the best tool for knowing the natural world. And I want to introduce you to another guy here. This is the last slide. Carl Sagan, one of my top 3 heroes. And he came up with something called a baloney detector kit. Kind of interesting. I've kind of usurped it, and I call it my BS-o-meter. Basically, it's rules for how to engage people to know if they're full of crap, but also to know whether an idea has true merit, whether it's scientifically sound. Number one, independent confirmation of facts. And by the way, you can print this out if you want and tape it to the back of your door, okay, so that you see it every time before you leave the house, but you're not going to need to know this for a midterm. So this particular slide, keep it, for your own sake, but you don't need to memorize it. Number one, independent confirmation of facts. If somebody is telling you something and it sounds kind of strange, make sure that you hear it from a second independent person that has no connection to the first. That's always a good rule of thumb. Number two, encourage debate by proponents of all points of view. Never keep somebody out of the discussion just because you think that their idea isn't sound or valid. Everybody's point of view needs to be considered. No arguments from authority. That's right, in science, there is no such thing as an authority. At most, we have experts. Experts are people who study things their entire lives and probably know a little bit about that one particular subject. What's an authority? An authority is someone that tells you how to behave or tells you how to think. A great example of that, and authorities are everywhere, and in some cases it's good to have an authority. Here's a good example. My daughter, it's 9:30, and my daughter says, "Oh, I want to stay up and watch TV," and I say, "No, you need to go to bed." And she says, "But why?" And I say, "Because I said so." That's arguing from authority. That's an example of where authority is okay. Policeman tells you not to run a red light. Well, there's probably a good reason. He's arguing from authority. But in science, there's no such thing as an authority. We do not tell people how to think. If you don't like an idea, no problem. You have the scientific method at your disposal. Go ahead and test it yourself. But there are no authorities in science. Spin more than one hypothesis because, who knows? Your hypothesis may be right for now, but if somebody else knocks it down or is able to disprove it, make sure that you have a backup. Don't love your hypothesis too much. This happens sometimes in science where you hang your entire hat on one idea and then some hotshot scientist in Japan or India disproves your hypothesis, then you're all depressed. So don't love your hypothesis too much. Quantify wherever possible. Bring out your measuring tape, bring out your ruler. Always measure things in numbers. That you're always going to be better off doing that. Anytime you make an argument, all links in the argument have to make sense. They all have to work together. And if they don't, throw it out and start over. Here's another important one, Occam's razor. Occam's razor, if you've seen the movie Contact, if you haven't, that's your homework. Go watch the movie Contact. No, just kidding. It's a good movie, though. You should probably check it out. They talk about Occam's razor in there a lot. The idea is that suppose you have two hypotheses and you weren't able to disprove either one of them, but they conflict with each other. Then you tend to go with the hypothesis that is the simpler explanation. Occam's razor basically says that. Go with the simpler of the two explanations. And finally, can your hypothesis be falsified? Is it testable? Is it duplicatable? If it's not, then you need to start over. Okay, everybody, so that is our presentation on the merits of science, biology as a scientific endeavor. And make sure that you have read Chapter 1. This kind of coincides with sections of Chapter 1. You need to know that chapter, and you need to know this lecture. And everybody have a good week. Try those quizzes, and send me emails if you need any help. Stop by my office hours. Sometimes I get lonely in here. Take care.